So we know that the natural numbers is kind of an interesting, weird set because it's the same size as the even numbers, and it can be shown that it's the same size as the odd numbers. I'll leave that as an exercise for you. Not too hard to prove given the same technique that we just went through. But what is interesting is that we have more numbers. Historically, we think about the natural numbers as representing counts of stuff, right? But what about integers? Well, as it turns out in the history of math, a lot of people were realizing that we were missing numbers. We couldn't just work with 0, 1, 2, etc. We needed some notion of direction. For example, if I move 2 steps forward and then I move 1 step back, what is the quantity there that represents the back? It's not moving by 1 unit because I'm moving in an opposite direction. Here's another idea. If I give you $2 and you give me back $1, how do I represent that numerically? So historically, a lot of people were starting to realize, hey, you know what, there has to be more numbers. It can't just be 0, 1, 2. There's this notion of direction, right? This notion of giving some in the positive sense and taking some away in the negative sense. And so this is where the idea of the integers came around, which is denoted by z. And the integers are essentially the same thing as the natural numbers, except we put what's called a minus sign in here, which would represent some type of taking away of a count. And then we have the positive numbers, which represent some notion of a gain, right? Negative numbers mean I've lost money on my stock. Positive numbers mean I have gained money on my stock. So there's this notion of up and down, of take and give, back and forward, etc. The question, though, is now how many numbers are in this set? I mean, this has to be bigger than natural numbers, right? I mean, think about it. I have numbers in here that I didn't have before, but I have all the same numbers as I had before, right? I had the natural numbers, 0, 1, 2, 3. All those same numbers are in the collection of integers. So this has to be true, right? Actually, no. Why? Well, remember, if I can find a bijection, f, between z and the natural numbers, then those two sets have the same size. So what's that bijection? Let's do a count. Let's say we start at 0 and we go to 1, and then from 1, suppose we go to 2. I'm sorry, -1, and then from -1, suppose we go to 2. And then from 2, suppose we go in here, right, is corresponding to 0. This is corresponding to 1. This is corresponding to 2 and 3, and then 4, and so on and so forth. And as you can see, as I start to go out and out and out, I have effectively put the mapping between the natural numbers and the integers. How have I done that mapping? Well, again, just follow the movements, right? So this starts at 0, then 1, then 2, then 3, then 4, then 5, then 6, and so on and so forth. I think I did it backwards, but you get the point, right? But what is this? Notice all of the positive numbers here are being assigned to odd numbers, and all of the negative numbers are being assigned to even numbers, and 0 is assigned to 0. Therefore, I'm not going to prove it. You can prove this on yourself, but this mapping, this specific mapping, is a bijection between the two sets. And so very, very fascinating stuff. As it turns out, these two are the same size, and they're the same size as the even numbers, and they're the same size as the odd numbers. So What does all of this tell us? This says that the odds, the evens, the natural numbers, and the integers are all the same size. Very strange stuff. But, okay, come on. The rational numbers. What is a rational number? Remember what a rational number is. A rational number, A, is any number, actually I'm going to denote this by X. A rational number, X, is any number which can be represented as the fraction of two integers. If you don't remember that, well, there you go. So we denote this collection using the funny symbol Q, and it's the collection of all fractions of integers where A and B belong to the integers. All right, now clearly I need to have more stuff in here. Well, let's take a look first at the positive rational numbers, where the only ones we allow for the fraction are when A and B are both negative or when A and B are both positive. We're only going to look at those for now. It can be shown, I'm not going to prove it, but it can be shown that if you can find you can find a bijection F between the positive and the regular rationals here. I'm not going to go through that proof. It's out of the scope, but just take my word for it. There's a bijection between these two. Try to find it on yourself if you're curious. But let's focus first on the positives, right? Well, what are all, actually, I'm going to assume both of these are positive to make it even easier. So how can I list all positive fractions between A? Well, let's make a table, right? No, let A be denoted by rows and let B be denoted by columns. So I have 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. I'm going to ignore 0 for now. And I'm going to let this be the fraction 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on and so forth. In this row, it's going to be the top number changes to the row number, 2 over 1, and the bottom number is the column number. And so on and so forth. 3 over 1, 3 over 2, 3 over 3, 3 over 4, 3 over 5, and so on and so forth. I mean, you get the point. So the question is, have I listed all of the positive rational numbers? The answer is yes, I have. The reason is because with this table technique, I've basically found the one-to-one mapping between every possible number that's defined in this set and how I'm finding that number in this table. Put differently, there's a one-to-one correspondence between numbers in the table and numbers in this set here. The question is the size of this set the same as the natural numbers? Believe it or not, the answer is yes. How do I do that then? How is that even possible? Well, let's do a count of movements, right? Let number 1 be mapped here, and then number 2 be mapped here, number 3 be mapped here, number 4 be mapped here, 5, 6, 7, 8. I would have 4 over 1 here. 9. 10. 11. 12. 13. Oh, no, wait a minute. I was supposed to go this way. And then I go that way. And then I go up this way. So on and so forth. In other words, map the number 1 to this element, the number 2 to this element, 3, 4, 5, 6, and so on and so forth. And when you do this, I'm not going to prove it, but it should be pretty self-evident that the size of this set is the same as the size of the natural numbers. And because I claimed that the size of this, there's a bijection between these two, therefore, if there's a bijection between A and B, and there's another bijection between B and C, this means therefore, exists a bijection between A and C. That should be pretty straightforward. Well, there's a bijection between these two, and there's a bijection between these two. Therefore, the size of the rational numbers is the same as the size of the natural numbers. So our intuition is really, it's gone out the window. As we're adding more numbers in here, into our number systems, right? We started with the natural numbers, and on top of that, we built out the integers, and on top of that, we built out the rational numbers, and so the natural numbers are a subset of this, is a subset of this, and they're proper subsets, by the way, and yet they all are the same size. But what about irrational numbers? What's an irrational number? It's any number that can't be denoted as a fraction of two integers. So for example, I can't represent the square root of 2 as a ratio between two integers. Why can't I do that? Small side proof for that. Assume I could do that. Then, and assume that A and B don't have any common factors other than just 1. So, put differently, they don't share any common factors, right? So, assume that this is true, that square root of 2 is a rational number. Well, move B on this side, right, and multiply both sides or square both sides, and I get A squared is equal to 2 times B squared. But if A squared is an even number, we know that A needs to also be an even number, and therefore there exists a K such that A is equal to 2 times K. If we plug that in here, we get 2 times B squared is equal to 4 times K squared, right? Divide both sides by 2. I get B squared is equal to 2 K squared. And B squared is an even number, 2 times a number, right? And because the square root of B is even, that means B also must be even. And therefore, there exists a K2 such that B is equal to 2 times K2. But hold on. Notice I have a 2 here in B, a 2 here in A, but I assumed they don't share any common factors. Yet I just found one. This is what we call a contradiction. And in math, when we reach a contradiction, it means that something we assumed must be incorrect. What did we assume here? We assumed that the square root of 2 can be equal to 2 integers which don't share any factors. And yet, we've reached a contradiction. That means this is not true, and therefore, there's more numbers or more stuff that we didn't consider. And therefore, if we go back to our number system, historically, people had found, I think it was I don't remember how one represents the irrational numbers, but basically, the irrational numbers are their own collection of numbers. They're numbers that don't belong in the rationals. So we really have 2 types of numbers, rationals and irrationals. The question is then, is the size of the rationals the same size as the irrationals? To answer that question is a little bit complicated, but to answer a different question is actually easier. If we define the real numbers, okay, which going back to here, we have what's called the real numbers, which is the collection of all the irrationals and rationals. The real numbers is just the union of the irrationals and the rationals, right? The question then is the size of the rationals the same as the size of in other words, is it the same as here? If it is, then as it turns out, there's only one infinity. And rationals are quite different